This is our first section, Chapter 6. Chapter 6, the book calls it Applications of Trigonometry. And most of it is, not all of it is, some of it's just kind of different representations of things than what you're used to. But a lot of it is going to be applications of trigonometry. Like I said, the chapter 4 was just going to be the foundation for so much of the stuff that we're doing. All this stuff is going to rest upon our understanding of sine, cosine, and tangent. Um, so this picture will look very similar to the picture that we had in chapter 4, where we had an angle, and then we had looking at this terminal side right here where the angle ends up. We looked at a point on that terminal side. We looked at this right here is going to be called the magnitude of the vector. It's the distance from the origin to where this vector ends up. In chapter 4, we just called it the r, or the radius, but we're going to just be looking at those relationships in just kind of a slightly different way. In some applications. So vectors are used a lot of times in physics. So our goal with vectors is we want to represent something that has both a magnitude and a direction. So it has like some sort of size or quantity or number to it, but also there's some direction to it. And so the most common example is going to be velocity. And so you want to know the difference between velocity and speed. If you're dealing with physics and in calculus, this comes up a lot. So speed would just be a magnitude. Speed is just a number, a quantity. So like if you're driving your car, you look on the speedometer, it tells you a number for how fast you're going. That's speed, just a number, just a magnitude. But if you look at your speedometer, you have no idea what direction you're going. Are you going, north, south, east, west? Are you going forward? Are you going in reverse? You have no idea your direction. And so that's where we don't want to just use a number, a magnitude anymore. Now we want to use a vector that would have that magnitude, that would have the how fast, but would also tell you what direction. And so we call that velocity. Velocity includes how fast you're going and what direction you're going in. And we can represent that with a vector. We use it with forces as well. So a force, like if you punch something, or if a car runs into something else, a force, we're acting upon an object, and so we have both a magnitude, how powerful or how strong you're punching something, you're hitting something, but also what direction. Are you hitting it forwards? Are you hitting it on the side? Where is the force acting, in what direction? Um, so we have both a quantity and amount, a size, the magnitude, just a single number for how powerful it is, but we'd also look at direction. Okay, so that's the idea of vectors. We want to look at the magnitude is going to be represented by the length, how long this arrow would be. So vectors are represented by what we call directed line segments. So this arrow, it actually doesn't keep going forever. This vector starts and stops right here. And so the length of that vector tells you how big or how large the magnitude is, like how fast you're going or how strong the force is by how long this vector is. That's the magnitude. Okay. And then we'll also have an angle that'll be the direction of the vector. What direction you're traveling is your velocity, or what direction the force is acting. Okay. Now for us though, a lot of times we're just going to kind of look at these relationships mathematically. We're going to have an angle for direction, and magnitude is going to be represented by the absolute value of v for the vector. So the vector is v, but absolute value around it to represent magnitude. And we're going to look at the relationship between that and the x and y. So vectors often are written just with an x and a y with angle brackets around them. Okay, so like in this first problem, we're going to look at the velocity vector of a plane, and we're just going to give it to you. It's almost going to look like a point. Okay, and so what that means is it's the point that the vector goes to. If we start at the origin and end at that point, that's the vector. And so if it's parentheses, it's a point. If we use these angle brackets, it's a vector representing some sort of motion or force from the origin to that point. And so if we're looking at this picture that we've always been looking at. We can drop down the altitude here, say that this distance is the x. This distance is the y, and we look at all those relationships between the x and the y, the magnitude and the angle. And so one thing that we do before what we did was we said, all right, the cosine of theta would be the x over, we used to call it r, now we're going to call it magnitude. So cosine would be adjacent over hypotenuse here, so the x over the magnitude. What we do now is we say, well, we want to know what the x is, and so we multiply the magnitude over. If I do times the magnitude, then I get this equation right here. Okay, so these equations right here, so these are going to be, you're going to have four really important equations. These are the first two. These equations just come from your standard cosine and sine that you already knew. We just rearranged it slightly. We just took the magnitude, we took the hypotenuse, and we multiplied it over. All right, and you could do the same thing with a sine equation, and you would get this one. Okay, so the x and the y, when we read it, this is called component form. So one thing with chapter 6 is there is going to be kind of a lot more maybe new vocabulary, more terminology. Um, and so if you kind of pick up on the terminology, that the math is actually going to be a lot of stuff that you're used to. It's just kind of in a new construct with new vocabulary. Okay? And so then the magnitude, this just comes from the Pythagorean theorem. So if we did the Pythagorean theorem right here, we would have x squared plus y squared equals the magnitude squared. And so then all we did is we just square rooted both sides, and that gives us this equation. So that's your third really important equation here. And so one thing to notice here, just like before, we always call the hypotenuse positive. So magnitude is always positive. Your magnitude is always going to be positive. Okay? And then the last thing that we look at is tangent. So tangent of the angle is going to be y over x. So we're going to find the angle using the inverse tangent. The really important thing, though, is remember those inverse tangents. There's like an infinite number of angles that have any particular tangent. An inverse tangent just gives you one. So the inverse tangent isn't always going to give you the correct angle. We're always going to have to make sure that we check the quadrant. That's going to be really, really important. Okay, so we find theta with the inverse tangent, but we have to always make sure we check the quadrant when we do. Okay, so that's kind of a lot of intro there. If you're not sure what's going on here, just kind of hang in with me. Let's just do a few problems, and they're really not too bad. Okay, so let's say that we've got this vector, and we want to find the speed. Okay, so again, speed is the number part of it. It's the quantity, it's the magnitude. All we need to do here is find the magnitude. Okay. And so what we can do with a lot of these problems is we can just use the formulas. I mean, if you want to draw these things out and kind of refigure out all the formulas every time, you could. But magnitude, we can just go ahead and use this formula, square root of x squared plus y squared. So we're just going to do square root again. So these angle brackets here is just x comma y. It's like a point, but it's a vector. It's representing motion to that point. So x comma y. So we're just going to do square root of x squared plus y squared. And of course, you can definitely use a calculator for that. So we've got square root of 237 squared plus 428 squared. So the plane is flying at about 489 miles per hour. Okay? About 489.237 miles per hour. That's the speed, it's the magnitude. Right? If we drew this out, that would be the length of this directed line segment from the origin to that point. All right. So then the direction angle, again, we're going to use inverse tangent. We know tangent is y over x. So to find the angle, we're going to do inverse tangent of 428 over 237. Just make sure you remember to do y over x, right? Tangent is y over x. So we do inverse tangent of y over x. Okay. And then just make sure you know what mode you're in. You could do degrees or radian. Vectors we do often do in degrees. So I'll have my calculator in degrees here. Inverse tangent of 428 over 237. If you wanted to do radians, you could. Nothing says which way you would have to do it, so either way would be okay. So we could either say 61.025 degrees, or if you want to do radians, you could. Again, radians, you don't have to write any kind of unit. All right, so there's the angle. So again, really a lot of this is just going to come down to using these 4 formulas that I've highlighted for you here. If you want the angle, then you use this. If you want the magnitude, use this. Later on, when we want x and y, we'll use those formulas. All right. All right, so now what about if wind starts blowing? Okay, so this is how the plane is flying right now. What if the wind starts to blow the plane a little bit off course? Well, this is one of the reasons they like vectors a lot in physics, is it's really easy to combine things. All you do is you just add the plane and the wind vectors together. And you'll see in a second, it's really easy to add vectors. All right, so these are little, mostly arrows, but there's just like a half of the arrow at the end there. That's a symbol for vectors. In print, you'll see them bolded. So like vector V, the V is in bold, but when you write, it's kind of hard to use bolds when you write. I mean, I guess I could try to like really press down with my pen a lot and go over it a lot, but when we write, we use these little half arrows here. Okay. All right, so what we want to do is we want to add these 2 vectors together. All right, now pretend that you're the person that came up with vectors. You invented vectors, and you get to figure out how the math is going to work. Okay, you get to decide, how do you add 2 vectors? How do I add this x and y plus that x and y? Well, try to think what would be the easiest, most simplest, most straightforward thing that you could think of. And that's probably exactly what we do. The most easiest, straightforward, simplest thing would be just add the x's together and add the y's together, right? And that's exactly what you do, right? So if we want to add these 2 together, we just take the 237 plus the negative 12, and we add the 428 plus the 23. Just add the x's, add the y's. And so then my new vector is 225 comma 451. All right, so unless the pilot adjusts their course and adjusts how the engine is propelling the plane forward, this is going to be the new way that the plane is flying based on the wind blowing it off course. Okay, so the resultant velocity vector, that's the result, that's the endpoint, that's the new thing that's happening. All right. So let's kind of step away from the application now a little bit. That hopefully gives you a little bit of an idea of how these vectors get used in physics. Let's kind of step back to the abstract a little bit. Let's say we've got these 2 vectors here. And so one thing you might notice immediately is, what the heck is this I and j here? Where'd that come from? So this I and this j right here, this I is not the imaginary numbers I. I guess they ran out of letters in math, maybe, I don't know. They're using the same letter that has another common usage, but this I has nothing to do with that. So this actually, it seems like what the heck's going on, but actually all it is, this is just another way of writing vectors. That's actually just the vector 3 comma 4. Okay, so I and j are what's called the standard unit vectors. If you wanted to, really you don't need to know too much of this right here, just if you want to know why this is working here. Really all you need to know is that if you see this I and this j thing, the first one's the x, the I is the x, what's next to the j is the y, that these are the same. That's really all you need to know. If you want to know why, what it is, so unit can mean 1 in math, and so we've got vectors with a length, a distance of 1 just in the x direction or just in the y direction. And so if you had this ai plus bj, well, I is 1 comma 0, and then j is 0 comma 1. So this is what you would have. And the way that multiplying in vectors work is you just distribute. Again, pretend you were the one coming up with vectors. If you invented vectors and wanted to come up with the simplest, most straightforward way to take a number and multiply it to a vector, you would just distribute. And that's exactly what you do. That's exactly what they decided to do, whoever came up with vectors. So if I distribute this here, let's say, oh, this is supposed to be b here. Sorry. We've got b times j. A times I, and then B times J. So if I distribute, this ends up being A comma 0 plus 0 comma B. And then again, if you add the x's separately and add the y's, a plus 0 is a, 0 plus b is b. So that's kind of why this works. But again, don't worry too much about that. Just what's next to the I is the x, what's next to the j is the y. It's just another way of representing vectors. Again, a lot of chapter 6 is just going to be kind of new notation, new vocabulary, kind of new context. The actual math itself is not necessarily going to be anything that's that new or that different or difficult. It's just kind of wrapping your brain around the new symbols and the new words. So let's say that we want to do 3 times u. Well, again, all we do is we just distribute. 3 times u, we do 3 times -2, and then 3 times 5. So we just get -6, comma 15. If we want to add the two vectors together, we just add the x's and add the y's. So answer for number 1 is right there. For here, -2 plus 3 is 1, and then 5 plus 4 is 9. All right, that's it. Not too difficult. Right? What about combining them together? So, what if we want to do subtraction? Subtracting is just adding a negative, right? It's not really anything different. But what if we're combining, multiplying, and adding or subtracting there? Why don't you go ahead and give number 3 a try? It's a little bit more involved than what we've done so far, but again, it's just combining these two things together. Just watch out for we're a little bit mean here. We got 2v first and then 3u second, so watch out for the order of the vectors there. Don't let us trick you. But take just a minute and go ahead and give number 3 a try. See if you can figure that one out. All right, and there's the answer there, 12 comma -7. Just make sure you can handle the subtraction. For me, I find it easier to do plus the negative. If you wanted to actually subtract, you could, but just make sure you don't do the negative twice, right? You either multiply by +3 and then subtract, or multiply by -3 and then add, because your answer. All right, so now let's say that we want to find the magnitude and the direction angle for these vectors. Because again, remember that's kind of the point of vectors, is to have a magnitude, a number, a quantity, a size, and also have a direction. So if we write vectors this way, we want to still be able to know what the magnitude and the direction are. Okay. Well, magnitude we've already done. Again, magnitude is just square root of x squared plus y squared. So magnitude here. Again, a lot of it comes down to these 4 highlighted formulas here. You just want to know those 4 highlighted formulas. If you really need to, you can always draw the picture and you can figure them out again. But it's helpful not to have to derive the formula for yourself over and over again every time. A lot of this is plug and chug if you know these formulas. Right? So square root of -2 squared plus 5 squared. So 4 plus 25, that's square root of 29, and you could leave your answer like that if you wanted to, um, as long as the radical doesn't reduce, right? Or we can find the decimal, 5.385. Either way, either answer is fine, right? And then direction angle, again, we did that before. So for our theta, we want to use tangent. We know the x, we know the y, and we want theta, so that's tangent. We want to try to avoid using this magnitude, right? Because then maybe you're using this ugly decimal. You don't want to use rounded numbers in later calculations, right? So that's why we don't tend to use the sine or the cosine. The sine or cosine, we'd need to involve this hypotenuse, which we might be using that rounded decimal, which would be no good. We want to use what we started with, which was just x and y. We originally didn't know the hypotenuse. It's always better to use the given information. Maybe we messed up too. Maybe this was, maybe I added wrong. Maybe it was 28. So it's always safer to use the given information. So I'm going to use inverse tangent of 5 over negative 2. Remember, tangent's y over x. All right. Let's see, and I'll just do this in degrees. You can do it in ratings if you want. I'll just do these in degrees. So we got 5 over negative 2. And so we get negative 68.199 degrees. All right. Here's the thing, though, that's wrong. That's not the right angle. Is my calculator broken? Is that the no? My calculator's not broken. That's nothing in my calculator is incorrect, but my calculator is just a tool. We got to still use our brain with our calculator. We can't get too dependent on the calculator. Okay, remember this note right here. We have to check the quadrant. Okay, so take a look at this. Take a look at our original vector. Let's try to think about what that would look like. Okay, x is negative and y is positive. Well, if x is negative and y is positive, that's in the second quadrant. Our vector is supposed to be in the second quadrant, so our angle, our theta, is supposed to be here. That's supposed to be our theta. Last I checked, that's not what negative 68 degrees looks like. Negative 68 degrees, that would be down there. Negative 68 degrees would be a fourth quadrant angle. Okay? Those don't match. If they don't match, then it's not the right angle. Right? We need to find the angle that actually matches this original vector here. Okay? Well, what we know is that they have the same tangent. The tangent still has to be 5 over negative 2. So if they have the same trig value, they have the same reference angle. So this right here is the 68.199 degrees. All right. So then to find this angle that we want, we could take 180 and subtract the 68 degrees. 180 minus 68.199 degrees. Now the only thing is in my calculator, what I have is the negative 68.199. So what I'm going to do in my calculator is I'm going to add negative 68.199 degrees to get that subtraction there. I'm going to take that negative and add the 180. Okay, again, if I just hit the plus button, it'll put ants in there. You can take that answer, and that's actually the correct angle. That's the second quadrant angle that matches this picture right here. All right. So what I actually wanted was 111.801 degrees. Okay. Notice I skipped that step when we did an angle before, okay, because they did match up. This one, x and y were positive, and so that's in the first quadrant, and what I got right here was a first quadrant angle, and so they did match, so I was good to go. Okay, that's what I want. I want to have the angle and the vector in the same place. If they match, then I'm done. My calculator gives me the answer, I'm good to go. Okay? If what my calculator gives me doesn't match what I want, well, that's when I have to do a little bit more work. Okay? Don't just rely on the calculator. Make sure you use your brain as well. Okay, so I'm going to have you do the second one in just a minute. So what we did here is I gave you the x and the y, and we needed to find the magnitude and direction. What if we want to go backwards? What if we have the magnitude and the direction, and we want the component form? Again, component form just means x comma y. All right, so now we're going the other direction. Well, again, let's just kind of look at our four formulas that we've got. All right, we've got the magnitude and the angle. We want the x and the y. Which formulas would be most helpful? It would be these, right? This tells me the x when I know the magnitude and the angle. This tells me the y when I know the magnitude and the angle. All right, so the x is going to be the magnitude times cosine, just like with the unit circle, just like with everything else we were doing. X goes with cosine. Okay. And so just make sure you're still in degree mode. So we've got 5 cosine of 207. So negative 4.455. And then y will be the same thing, just sine instead of cosine. So I'll just use second enter. Second enter will bring back what I had before, and then just change the cosine to sine. There we go. Negative 2.27. And technically component form, I should write it with angle brackets. Let's go ahead and write this here. Negative 4.455, negative 2.27. There's the component form. All right, so why don't you go ahead and try a couple of these here. I'm gonna zoom out a little bit to show both of the problems. So this one here, we wanted to find the magnitude and the direction angle, and I'm telling you -1, -4 is the component form. And then the second one, now I'm telling you the magnitude is 6 and the angle is 150 degrees. And I would like you to find the component form for me, please. Go ahead and give those two problems a try. All right, so we can check our answers here. So for the first one, you should have found the magnitude was √17 or 4.123, and then your angle should have been 255.964 degrees. Make sure you checked your quadrant. Don't just rely on what your calculator gives you. Okay, we had to change the quadrant. Again, that won't always be the case. The very first one we did, the calculator did give us the right answer. Okay? Sometimes the calculator gives us the right answer, sometimes it doesn't. Okay? You've always got to check where that vector is. We always want what we start with and what we end with to be in the same place. Right? What we wanted was this third quadrant vector, and so we had to take 180 and add it to the reference angle that we had there. Right? Down on the second problem here, and again, you can just plug and chug in the formulas. You're welcome to use your calculator, plug and chug, you're good to go. 150 degrees actually has a 30-degree reference angle, so you could have known the exact values of the sine and cosine and done it that way if you wanted. You can also always draw these out and just use SOHCAHTOA. Like if you don't want to memorize the formulas, you can always draw them out. The thing to watch out for is remember to think about the negatives. So if you drew this out, and did SOHCAHTOA, what I'm going to get from a lot of people is just people saying that the x and y are always positive. Right? So make sure that, like, if you're using this reference angle to find the sides of the triangle, that you remember that left has to be a negative number. Okay? Down has to be a negative number. If you're drawing it out and thinking about triangles, don't forget to then think about, well, this is really x and y, and so they can be negatives. But it's a lot easier if you just use those formulas, just kind of plug and chug there.